Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about Bayesian parametric modeling. The prerequisites for this material are discrete and continuous random variables. The goal is to describe the framework of Bayesian parametric modeling. So let us remind ourselves first what we mean by parametric modeling. We talked about parametric and non-parametric modeling where we were discussing how to estimate the PMF or the PDF of random variables from data. One of the options was to go non-parametric, and for the PMFs just use empirical probabilities, and for the PDFs use either histograms or kernel density estimation, where we didn't make any assumption about the underlying shape of the PMF or PDF, other than maybe some smoothness assumptions when we estimate the PDF. This was problematic when we didn't have enough data. So what we said is in some cases, it's better to make some assumptions about the underlying probabilistic model, derive what kind of shape we expect for the PMF or PDF, let that shape depend on a small number of parameters, and then let's fit those parameters using data, typically by maximizing the likelihood of the model. Okay, so here's an example where you see the histogram corresponding to inter-arrival times at a call center, and we decided that an exponential model would be a reasonable way to fit it and actually fits the data rather well. The exponential model only depends on a single parameter. So this makes the estimate very stable when we don't have a lot of data. Okay, so that's just a brief reminder of what we mean by parametric modeling. The key idea when we're doing Bayesian parametric modeling is that we interpret the parameters themselves, this lambda that the exponential depends on, as random variables. Before, right now when I was talking about it, we just consider them as as a fixed constant that we had to estimate from the data, and that was it. Now we're actually going to endow, who knows, these parameters with their own distribution. This will become clearer when we look at an example. So the idea now is that we're going to decide, we still need to do the parametric modeling part where we decide what is the parametric model that is adequate for this problem, and that is going to be ad hoc. It's going to depend on the problem that we want to model. That parametric model is going to have a certain parameters. We're going to say, oh, those parameters are actually going to be random variables. Then we're going to have some data, and in order to do the Bayesian parametric modeling, now there's going to be additional design considerations. So we're going to have to decide what the prior distribution of the parameters is going to be. What's typically the PDF? We typically model the parameters as being continuous. And then on top of that, we still have this parametric modeling that I was referring to before, where we want to say, okay, given the parameters, if we fix the parameters, what should be the shape of the PMF or the PDF? Okay, and here this is typically the same as before, right? Because if you're conditioning on the parameters, this conditional is going to be what we actually before were interpreting as the parametric PMF or the parametric PDF. The difference now is that it's a conditional because the parameters are random variables themselves. So if we think, for example, if we're modeling inter-arrival times, now this conditional would be the one that is exponential, and the parameter would no longer be a constant that determines the shape of that exponential. It would be a random variable itself. The ultimate goal is to compute the posterior distribution of the parameters given the data, which is very useful, right? Because now we're going to see how uncertain we are about the values of the parameters, which is something that is more difficult to do in the traditional way of doing parametric modeling, although you can also, and we'll talk about that. You can also put some confidence intervals on the value of the parameter. We're going to talk about that more in the future, but this gives it to you directly, which is kind of nice. It also enables you to incorporate the uncertainty that you have about the parameter. So let's illustrate this with a very concrete example. So imagine that there's going to be a coin that is going to be flipped, and we want to determine whether what's the probability of heads when you flip this coin? Because it could be that it's not a fair coin. In fact, we suspect that maybe it won't be a fair coin. So we want to determine that by observing the result. Okay, so we're not sure whether the coin flip is fair or not. We're going to model the probability that the coin flip is heads with a parameter. Okay, we're going to, actually, I shouldn't have said that and then asked you the question. So how are we going to encode the uncertainty about whether the coin flip is heads or not? Sorry about that. We're going to use a parameter. Okay, that was terrible. Okay, so we're going to use the prior distribution of this parameter, which captures the probability whether the coin is heads or not. So if you like, let's talk about this a little bit more technically. We're assuming that the coin flip is given by a Bernoulli distribution conditioned on the parameter of the Bernoulli, which is this parameter theta. Okay, and that's what we're going, like that parameter theta, because we're in a Bayesian framework, we're going to model it probabilistically as a random variable. Because we're not sure what theta is like, maybe we don't even have like any expectations about whether the coin would be more tilted towards 1 or tilted towards 0, we're going to just say, okay, theta is uniform, okay? This is our, we have a lot of uncertainty about what's up with this coin. This is what we believe that theta could be anything between 0 and 1. Okay, we give it a uniform distribution. This is a choice of the modeler, of you as the Bayesian modeler. If you decide to use Bayesian parametric modeling, you're going to make this choice. Okay, so now we've made this choice. And now we actually flip the coin. We gather some data by looking at what the coin does. And it turns out that the coin lands on tails, which in this case means 0. So now we want to update our uncertainty about the parameter. So this is our uncertainty about the parameter before flipping the coin. Now we have flipped the coin. We're assuming that the coin is flipped according to a Bernoulli conditioned on this guy. So how are we going to update our uncertainty about the distribution of theta? Well, what we're going to do is we're going to apply this formula that we derived when we're talking about the joint distribution of discrete and continuous random variables. So remember that the product of the marginal of a continuous random variable and the conditional of a discrete kind of acts like a joint, like it captures the joint distribution. In order to get the conditional, we divide by the marginal of the discrete at that value. Okay, we proved that this actually holds. So in this case, let's look at it carefully. What are all these values equal to? This is the prior distribution of the parameter. So this is just a uniform. Okay, so between 0 and 1, this is just going to be equal to 1. Here, this is a Bernoulli random variable conditioned on theta, right? What's the probability of 0 conditioned on theta? It's just 1 minus theta. So this is just going to be 1 minus theta. Now this one might look a little bit trickier. How do we compute the probability of 0? Well, we need to first condition on theta and then integrate over theta, right? Because all we know is the conditional distribution of the coin flip R. Now I'm wondering why I used R for the coin flip, but that's what I used, so let's go with it. Now we only know the conditional of R given theta, so we need to integrate. Okay, it's going to be equal to the integral of the conditional times the marginal. And now that marginal is equal to 1, so we're going to basically integrate 1 minus theta from 0 to 1. That's what's going to happen. Alternatively, basically what are we doing here? We're just normalizing this so that it's actually a valid PDF, as usual when we compute conditionals. Okay, so that's the integral from 0 to 1 of 1 minus u, and that's equal to just 2 times 1 minus theta. So let's plot how this posterior distribution looks like. It looks like this. So this is kind of interesting, right? We observed a 0, and this makes us change our minds. Now we think that, theta is probably more towards 0. This is only a single data point, so there's still a lot of uncertainty, right? Otherwise, this would be super peaked, but it's not at all, right? So there's plenty of uncertainty, but, the Bayesian model tells us like, yeah, we saw tails, let's shift, the distribution more towards 0, okay? And realize that now it cannot be exactly, like around 0, it has become particularly small because, it would be unlikely to see, around 1, it has become particularly small because it's unlikely that we would see a 0. Here it's peaking more. Okay, so long story short, the posterior, which is here in red, kind of shifts towards 0. because of the data. Okay, so now let's think of a case where maybe you don't trust whoever is flipping the coin. They're trying to bet you that the coin is going to be, they're trying to bet money on the coin being heads. So you're like, I'm going to be careful about this. I think, I have this prior idea that probably the coin is more towards heads. Or maybe you have additional previous information that you have observed about the coin, and you have condensed it into this uncertainty about the probability that the coin is heads. Okay, and you could do this, for example, in an election. You have been following a candidate, and you integrate all the information that you have about them in a certain distribution about the probability that they will win a certain state or not. For example, you could do it like this, right? Like this is how you could build your prior. So in this case, again, we're kind of suspecting that the probability is going to be more towards 1, so we're going to have that prior. So how does this change things? Again, we have the same situation. We land on tails. So we're going to do exactly the same thing, right? We're going to go and compute the conditional of theta given this observed data. Exactly the same formula. What changes now? What changes now is that this now is no longer equal to 1 between 0 and 1. It's actually going to be equal to theta, because realize that this is just linear. It's actually 2 theta, so it integrates to 1. Okay, so this is going to be equal to 2 theta. And now when we compute this guy, we have to integrate 2 theta over 0, 1, right? So here we're going to have to integrate 2u times 1 minus u. Okay, so that's how the previous calculation has to be modified, because we have modified the prior on our parameter. When we plug that in, we get this expression. You do the integral. It's not too difficult, even for me. And you get 6 theta times 1 minus theta. Let's plot and see how our posterior looks like in this case. And the posterior has shifted again. But interestingly, because we started more towards the right, now it hasn't shifted as much as in the case where we started with a uniform prior, right? Like it has become quadratic just because of the shape of the prior and the conditional. It has shifted towards the center. This is important because now you realize that your posterior looks very nice, right? It gives you the probability, that the coin is going to be heads. Like, what's the probability? Like you can compute a lot of probabilities with this, but those probabilities do depend on your prior. This posterior can look very different depending on your prior, so you might want to you might want to check how the posterior changes depending on the prior, and you might want to be careful about it. Okay, so Bayesian modeling is great because it allows you to incorporate your prior assumptions, but if some of those prior assumptions are wrong, they might propagate to your conclusions. So it's, because sometimes you see a distribution and you're just tempted to say, well, that is the distribution, that's it. I got a probability, let's go home. It's obviously going to depend on modeling, okay? It's important to bear that in mind. Okay, so in general, this procedure that we have carried out where you model a probability using a continuous distribution, this is something that we do all the time in probabilistic modeling. A very popular distribution to use in order to model a probability is the beta distribution, which is an unimodal distribution. It means that it has like a single peak, and that peak depends on 2 parameters, A and B. Okay, just on those 2 parameters. The form of the distribution is like this. So you might realize that if we set A to 1 and B to 1, we just get a uniform distribution. We're going to see in a moment. It's not, super quick to see, but it happens. If you take A equals to 2 and B equals to 1, then you get a triangular prior like the one we have used. If you take A and B bigger, you start getting like a unimodal distribution. I'll show you in a moment. This normalizing factor here is just this integral, which is tabulated, or you can use a computer to compute it. Like, it's just a normalizing factor. That's why it's called the beta distribution. Okay, so beta distributions look like this. So for example, if we're very, very uncertain about the parameter, we're going to use maybe something like this, where it's uniform. Okay, that's 1 and 1. If we're very sure about our, the value of the parameter, we might peak it at some point. So here for A3 and B15, we get this. Okay, and this can be shifted for different choices of A and B. Okay, so basically, if you want a prior where you're saying, oh, I think my probability, let's say, is around 0.1, and you want to decide how peaked it is around 0.1, the beta distribution is a great choice. Okay, so now in our previous example with the coin flip, we had a single data point. It was great because it allowed us to understand the steps in Bayesian modeling very clearly, but you're always going to have more data, right? So what if we have more data? A common assumption is that once we fix the distribution of the parameters, the data are going to be conditionally independent given the parameters. So we have a coin flip given whatever is the probability of heads. Given that probability of heads, we often assume that the observed data points are independent. If we're thinking about how many people vote for a certain candidate, given the probability that that candidate wins, given the fraction of people in the population that want to vote for that candidate, we assume that each person is voting conditionally independent given that probability. This is exactly the same as when we're having IID assumptions in our previous probabilistic modeling where the parameters were constants. This is why when we're doing maximum likelihood, the likelihood would factorize into a product and the log likelihood would separate into a sum. Okay, so in that sense, this is really, really similar. Again, the main difference is that now this likelihood is a conditional because the parameters have their own distribution. Okay, so this is what happens when we look at the conditional of the data given theta. It factorizes into the condition of each data point given the value of the parameter. Okay, under those conditional independence assumptions, which again are super common. The same if we're looking for a conditional, like if we are fitting, a continuous distribution, like in the case of the inter-arrival times, for example. Okay, so let's imagine that we want to estimate the parameter of a Bernoulli distribution, which is, we do it very often, for example, in elections, if we have two candidates. We have a sequence of n binary outcomes, 0 or 1. So this could represent someone voting for one candidate or the other. Okay, and now we are going to model the parameter theta as a beta distribution with parameters a and b that are going to depend on all our previous information that we have gathered. If it's an election, like all the previous polls, or maybe results in previous elections, or our gut feeling based on what we read in the newspapers, which is probably useless trash, but who knows, we might want to take it into account. Then, given the value of the parameter, each data point is going to be Bernoulli with parameter theta, and they're going to be conditionally independent, okay, given the value of the parameter. Okay, so now let me ask you a really stupid question given what I just said. The distribution of ones if the data... sorry. Actually, I thought I was going to ask you now, like, do you think the data should be conditionally independent given theta? Anyways, let's move on. What is the distribution of the number of ones if the data are conditionally independent given theta? What's the distribution of the number of ones? It's binomial, right? Because they each have the same probability theta, and they're all conditionally independent if we fixed that theta. So we have a binomial. Okay, binomial with parameters n and theta. Great. So now, how do we update the prior distribution? So again, we have this prior that is beta, so it's going to be peaked at a certain point depending on what our prior assumptions are, then b. How do we update it? So we apply the same formula again. We say the prior of theta times the conditional has to be divided by the marginal over the data. So now this is going to be this beta distribution. This is prior on the parameters of theta. This is the binomial likelihood. And here we're just going to have to integrate this whole thing so that the conditional actually is a real condition. Okay, so that's why I have this integral here, because we want the marginal of the data. So we need this normalizing constant. Okay, so let's plug things in. Again, here we're going to plug in the beta distribution. Here we're going to plug in the binomial. Okay, we plug in the beta distribution here. We plug in the binomial here. And down here, we have exactly the same expression, but we're integrating it because, again, we need this to be normalized. And now, what we realize is that we can cancel some stuff out. Because here the integral is over u, right? So in particular, this is just a constant. So this can be cancelled out with this, okay? And we also realize that we can merge some stuff up here. So here we have theta to the a minus 1, theta to the x. If we multiply these two things, it's just theta to the a plus x minus 1. And same for 1 minus theta, this is just 1 minus theta to the b plus n minus x minus 1, right? So we can merge that together. And what do we get? Well, this is exactly a beta distribution, but with different parameters. The parameters have been updated to be x plus a minus 1 and n minus x plus b minus 1. Okay, and this is going to govern how the beta distribution is updated. The really cool thing is that the posterior is also beta. So we can just update the parameters directly without having to go through this once we have shown that this is the case. So, you get the beta distribution with these new parameters as the posterior. Let's, make sure we understand what we have just proved. If we have a sequence of n binary outcomes, 0 or 1, again, it could be that a candidate wins a state or not in an election. Not a candidate, each voter votes for a candidate or not in an election. That's what I meant by the sequence of binary outcomes. We have a prior that is beta with parameters a and b. We have a likelihood or a conditional distribution given the parameters, which is Bernoulli with parameter theta, which translates to the number of ones being binomial with parameters n and theta. If that is the case, then the posterior is just going to be beta with parameters x plus a and n minus x plus b, where x is the number of ones. It's super easy to update. The fact that the posterior and the prior are the same is just because of the special shape that beta, the special function that beta and binomial distributions follow, right? Because we can do these cancellations. In Bayesian statistics, this is known as the beta distribution being a conjugate prior for the binomial likelihood. Because if you have a binomial likelihood, you update your beta and you have a beta distribution as a prior. You just need to update the parameters because the posterior is always going to be beta. Okay? And there are other conjugate priors in Bayesian statistics. Let's apply our result because this has been a little bit abstract because we can't visualize how the beta distributions actually change. In order to visualize that, we have to look at actual data. So let's look at a real poll in Pennsylvania from the 2020 election. It turns out that in this particular poll, which was not like an amazing poll according to 538, I just chose it a little bit at random, 281 people intended to vote for Trump and 300 intended to vote for Biden. Some other people were undecided. You definitely need to take that into account when you're deriving conclusions for the poll. You also have to take into account what the demographics of the poll, because obviously if you do the poll in an inner city as opposed to doing the poll like out in the countryside, the conclusions for the whole state are going to be very, very different. We're not going to worry about that, okay? Let's just assume, 281 people intend to vote for Trump, 300 intend to vote for Biden, end of the story. Okay, so we want to model the fraction of people that intend to vote for Trump using this random variable theta, which again is a parameter of a Bernoulli, right? It represents the fraction over the whole population of people that want to vote for Trump. So if n people are chosen independently at random, which is what we're going to assume was happening in the poll, this is unfortunately not the case in real polls, which makes life of data scientists very, very tough. But for the purpose of this example, we're just going to assume it. If n people are chosen independently at random with replacement from the population, what is the likelihood of x of them voting for Trump? So I pick someone at random, they vote for Trump or not. I pick someone else at random, and I pick n of them. For each of them, the probability that they will vote for Trump is theta. So conditioned, and actually I should have said this, conditioned on theta, what is the distribution of the number of people that are going to vote for Trump? it won't come as a surprise probably. It's binomial. It's binomial conditioned on theta. It's binomial with parameters theta, n and theta. Okay, n because we're choosing n people. So we're exactly in the situation that we were talking about previously. I can assume a beta distribution, which I am going to choose, and then I can update them. I can update it with this data. And I know that the posterior is going to be beta with the new parameters. Okay, the posterior distribution obviously depends on the prior. If the prior is beta with these parameters, then the posterior is going to be beta with these parameters, a plus 281, b plus 300. Okay, according to the result that we just proved. But again, just let's take a look. It's always important to look at concrete examples and see what the actual effect of the stuff that we prove is on real data. So what is the probability that Trump wins in Pennsylvania? Let's say that all the data we have is this poll. We imagine that this poll is hopefully, contains a random sample from all of Pennsylvania. How do we use it to actually predict who wins in Pennsylvania? Well, what we're going to say is, well, what's the probability that theta, which is the fraction of people that are going to vote for Trump, is above 0.5, right? This is what we want to find out. And we want to condition on the data that we observe. Okay? So now we know that this conditional distribution is going to be beta with these parameters, is what this conditional distribution is going to look like. So now I'm going to give you some examples showing how this changes depending on the prior distribution. So the prior distribution is going to be this dashed line. Here, I am looking at a scenario where we think that Trump might win. This is why this is centered here, but we're not very sure. So things are super uncertain. Like this is why this, is so extended here. If we do that, then we end up with this. So the posterior distribution is given by this peak. So just to be clear, it's this solid line. This is what we get when we update the parameters of the beta. It's much more peaked because we have a decent amount of data. Again, assuming that the data is uniformly distributed in all of Pennsylvania, which is a strong assumption, but still, it becomes much more peaked. And according to this prior, when we update the posterior, there's an 80% of probability that Biden wins, because even though the prior is, what am I saying? Sorry, I actually said that wrong, right? Because this is towards the left. So here we actually thought that Biden was favored, which actually was the case when I was looking at this poll originally. So we think that Biden is favored, but we're not sure at all. Under that prior, when we update the posterior, Biden has 80% of winning in Pennsylvania. And this, this posterior is given by A equals 4, B equals 6. What if, we're not very sure and we actually don't know who is going to win? So we're being super agnostic here, super conservative. We're saying we don't know. We're just going to use something that is very flat and is centered at the beginning, at the middle. So we see that actually that 80% was pretty robust to the choice of where the prior is centered, right? We still get around 80% that Biden would win according to this poll when we update the parameters of the beta distribution that we're using to represent the uncertainty about the fraction of people that would vote for Trump. And by the way, that's why we have 0.5 here, right? We need to integrate the posterior. I should have said that a bit more clearly, right? We have this posterior that is the solid line. We need to integrate it up until 0.5 to get the probability that Biden wins. The probability that Trump wins can be obtained by integrating from 0.5 to 1. So here we think that Trump is favored to win, but we're not sure at all. If that is the case, if we apply that prior, the probability for Biden goes down, but not by that much if there is this level of uncertainty. So from the results in the poll, again, under the strong assumption that we have randomly selected voters from all of Pennsylvania, things are looking good for Trump if we were uncertain before the poll. Because we have gone from 80 to 78 to even 75 when we were favoring Trump in the prior. What if we're more sure? Here we're pretty sure, that the fraction of people that will vote for Trump is around 40%. If that is the case, then the posterior tells us, no, don't be so sure. We need to shift this more towards the middle because that's what the poll indicates, but still it doesn't shift it so much that Biden loses that much probability, and that this prior actually would be pretty sure, looking at the posterior, that Biden would win Pennsylvania. And there are prior that is centered, okay, where we say, oh, we think actually that they're very, very close in Pennsylvania, and we're relatively sure of that, so this is why the prior is more concentrated. If we observe this poll, then we would be like, oh, it turns out that maybe we should, maybe Biden would win. If we're pretty sure that that Trump is actually favored in Pennsylvania, which is represented by this prior that is more peaked around 60%, then the poll would tell us, don't be so sure, it's actually going to be very, very close according to this data and according to your prior. Like if I put the data and the prior together, it's actually going to be pretty, pretty close under the assumptions of this model. If you're very sure, if you have a prior that is super sure, so this is a super peaked prior like this one, here we're very sure that Biden is going to win, the data might shift it a bit, but it's going to be difficult for it to shift it a lot if you don't have a lot of data. Right, these are reflected here. Here we're almost sure that it's going to be 50%. It shifts it toward Biden by not that much. Here we were very, very sure that there's 60% of people that want to vote for Trump. We don't have enough data to shift the distribution below 0.5, so we still think that Trump will win. So the prior really, really influences our conclusions. So what have we learned? We have learned about the Bayesian framework for parametric modeling, where we endow, I don't know why I repeated that word again, given that I don't know how to pronounce it, where we interpret the parameters in parametric models as random variables, which enables us to observe their posterior distribution after we have observed the data. It also enables us to incorporate assumptions about the problem or previous information through the prior distribution of these parameters, which is then updated with the data. Thank you very much.